Welcome back, Focus learners, to another Masterclass Explainer. Today, we are embarking on a high-stakes scenario that I like to call the space mission. I want you to imagine, just for a moment, that you are sitting at the primary control desk of a multi-billion-dollar satellite launch. The countdown is literally ticking down in front of you. In a scenario exactly like this, there is absolutely zero margin for error. Every single calculation, every single data point must be 100% perfect for a successful launch. Just one missed decimal point, one flipped negative sign, or one misunderstood directional vector, and that incredibly expensive satellite is completely lost to the void of deep space. Well, listen up, because your Cambridge physics examinations, and it doesn't matter whether you're sitting for syllabus codes 0625, 0652, 0654, 0972, 5054, or even 9702, are exactly like that space mission. The Cambridge examiners, they are your mission control, and they are relentlessly looking for absolute, uncompromising precision. So today, we are going completely hands-on. We're going to build your ultimate foolproof physics toolkit with a laser focus on mastering uncertainties and vectors. But we aren't just going to dryly look at the theory. No way. We are going to look at how real students actually tackle these problems in the exam hall and exactly why so many of them hemorrhage marks. Let me introduce you to two typical students we see all the time in our strategy sessions. First, there's Alex. Now, Alex is brilliant at memorizing. Seriously, a walking textbook. But in the exam, Alex overloads every single answer with raw physics facts, writing massive rambling paragraphs of text, but completely misses the actual analysis the examiner asked for. Then on the other end of the spectrum, there is Sam. Sam is an absolute speed demon. Sam rushes through the paper, glances at the numbers, and completely misses the specific, rigorous requirements of the command words. By the end of this explainer, you are going to see exactly how to avoid the deadly traps that Alex and Sam fall into and how to structure your answers for absolute maximum marks. Let's get into it.
Let's kick things off with the classic, real-world challenge. This is the exact type of physics question that pops up on past papers to immediately challenge your intuition and see if you're really paying attention. Here's the scenario. An athlete runs a 5-kilometer race. They are sweating, they are completely exhausted, their heart is pounding, and they have clearly covered a massive amount of physical ground. But a physicist looks at them, checks their clipboard, and says, "Actually, your final distance from the start is 0. So I want you to think about this. How is this mathematically and physically possible? When our student Alex sees a question like this, the panic sets in. Alex immediately writes a massive half-page paragraph explaining the biological kinetic energy expended, the average speed of the runner, and the friction coefficient of the running track. Tons of facts, 0 marks. Sam, on the other hand, barely reads it, just scribbles down the word circle and furiously turns to the next page. Also 0 marks. Both of these students lose the majority of the marks available because they are missing the fundamental toolkit required to actually analyze the physical world the way Cambridge wants them to. They are ignoring the command words and the core physics principles.
And here is the reality check, the crucial detail that makes all the difference. Although the athlete genuinely runs 5 kilometers in the race, his final distance from the starting point may well be 0 for one simple reason. He ran on a closed track and finished at the exact same coordinates where he started. This right here sets up our absolute core theme for today. The vital, non-negotiable difference between a scalar quantity like distance, which just measures how much total ground was covered regardless of where you end up, and a vector quantity like displacement, which cares intimately, specifically about your direction and your final position relative to the origin. Direction fundamentally changes how we measure the physical world. It's the difference between a successful space mission and a crash landing. If you want to secure those top-tier marks and watch those red pen crosses transform into green check marks, you can't just know the dictionary definitions. You have to apply what we call the Peel framework. Point, evidence, explanation, link. Here's how a top student does it. You make your point. The track is a closed loop. You provide evidence. The start and finish lines occupy the exact same physical coordinates. You explain the physics. Displacement is a vector quantity dependent solely on final position minus initial position. And finally, you link back to the specific question asked. Therefore, the overall displacement is 0 despite the 5-kilometer scalar distance covered. Boom! That is how a top-tier student constructs an answer. No fluff, just pure physics strategy.
Okay, let's quickly review our flight path for today. We are going to cover calculating extreme uncertainties, differentiating scalars versus vectors, adding vectors together, and finally, resolving vectors into components.
Section 1. Calculating extreme uncertainties. Let's fix the math.
In literally any laboratory experiment you do, or any data analysis question that pops up on your paper, there are going to be measurement errors. It's unavoidable. Instruments aren't perfect, and human reaction time certainly isn't perfect. Often, students get completely hopelessly bogged down trying to remember complicated fractional or percentage uncertainty rules, especially when they're dealing with complex equations that have crazy powers and square roots. When the command word on the exam clearly says calculate the absolute uncertainty, our rushing student, Sam, usually just guesses a random percentage to save time. Meanwhile, Alex writes out an entire page of complicated tangled algebra, gets completely lost in the math, and ends up with a completely illogical number. We are going to completely replace that chaos with a streamlined, zero-error strategy. Your secret weapon here is the extreme value method. If you ever find it difficult to deal with those messy fractional uncertainty rules, you can easily and accurately estimate the uncertainty by substituting the extreme limits of your measurements straight into the equation. It's a foolproof three-step recipe. Step 1. Calculate the absolute highest possible value for your final answer. You do this by taking the absolute upper limits of the numbers that maximize the result and the lower limits of any numbers that divide it. We call this our x high. Step 2. Calculate the absolute lowest possible value, or x low, by doing the exact opposite. Step 3. You simply subtract your lowest value from your highest value and divide the whole thing by 2. This method is brilliant because it turns a terrifying algebraic nightmare into basic primary school arithmetic.
Let's actually look at this extreme value method in action with a classic scenario, a simple pendulum experiment. You're trying to find the uncertainty in the acceleration of free fall, little g. Now, the equation for g involves the length of the pendulum divided by the square of the time period. Squaring an uncertainty, that's where people usually make mistakes. But watch how easy this is. If you want the lowest possible value for gravity, your g low, you just substitute the lowest possible measurement you took for the length and divide it by the highest possible measurement for time. Let's say after crunching those extreme numbers, that gives you 9.1 meters per second squared. To get your highest value, your g high, you use your highest recorded length measurement and divide by your lowest recorded time measurement. Let's say that spits out 10.3 meters per second squared. Now apply our step 3 rule. 10.3 minus 9.1 is 1.2. Divide that by 2, and you get exactly 0.6. Your final uncertainty is simply plus or minus 0.6 meters per second squared. In your exam, using that Peel framework we talked about, you clearly show these two extreme substitutions as your concrete evidence, and you state the final division as your clear explanation. It's clean, it's undeniable, and it scores full marks from the examiner every single time. Before we continue to the next crucial strategy, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Awesome. Let's keep this momentum going into Section 2. Categorizing quantities into scalars versus vectors. I really want you to think about what extra information is needed to fully, comprehensively describe an object's motion in space. If I tell you a car is traveling at 100 kilometers per hour, I've given you a magnitude and a unit. That's a great start. But if I ask you exactly where that car will be in 1 hour's time, you literally can't tell me. You don't have enough information. You absolutely need to know the direction of travel. This is the exact spot where our student Alex bleeds marks. Alex will define a physical quantity perfectly, quoting the textbook word for word, but when asked to actually predict an outcome or calculate a final state, completely forgets to apply the direction. As we can clearly see categorized here, a scalar quantity can be described fully, 100%, by giving just its magnitude and its unit. Mass, speed, energy, these are scalars. They can be added together algebraically, like you're counting apples. 10 joules of energy plus 5 joules of energy is always 15 joules. But a vector quantity, it has magnitude, a unit, and a direction. Weight, velocity, force. These cannot just be added algebraically in a simple, straightforward way. Notice the really subtle traps the examiner set up here. Mass is a scalar, but weight is a force acting downwards towards the center of a massive body, making it a vector. Speed is scalar, but velocity is vector. When you write your exam answers, you must explicitly state the direction for vector quantities. If a command word asks you to determine the velocity and you only write 15 meters per second, you will absolutely lose the final accuracy mark. You must write 15 meters per second due east or acting downwards. Direction is not optional, it is fundamental.
Now, here is a brilliant, slightly sneaky trick question pulled straight from the source material, and it's one that trips up our rushing student Sam every single time it appears on a paper. Think about it. Is electric current a vector quantity? Sam looks at this and immediately thinks, well, obviously. We literally draw arrows on circuit diagrams. Current flows from the positive terminal to the negative terminal. It visibly has a direction, therefore it's a vector. Sam writes this down, feels great about it, and loses the mark entirely.
Why? Because while we do conventionally give current a direction in wires, especially when we're using right-hand rules to predict magnetic fields, electric current does not follow the mathematical laws of vector addition. If you have two wires carrying 3 amps and 4 amps, and they meet at a junction, the output is always unconditionally 7 amps. It doesn't matter if those wires meet at a 90-degree angle, a 45-degree angle, or head-on. Because it adds together like normal everyday algebra, electric current must be treated as a scalar quantity. Always be on the lookout for these specific syllabus exceptions. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at Ace the Exams IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to at Ace the Exams IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Section 3. Adding and subtracting vectors. This is where things get truly dynamic.
We've firmly established that vectors demand a direction. This means that combining vector quantities is the point where normal, everyday algebraic addition simply falls apart. It won't work. We need a completely new strategy. We have to understand exactly how vectors interact when they collide, when they push against each other, or when they act at strange diagonal angles. Let's vividly contrast simple scalar addition with the beautiful complexity of vectors. Adding scalars with the same unit is no problem at all. If you have a 250 cubic centimeter beaker of water and you pour it into a 9.0 liter bucket, which, remember your conversions, is 9,000 cubic centimeters, you get a total volume of 9,250 cubic centimeters. It's guaranteed. It's basic math. But adding vectors, that requires knowing the direction. If I apply a 30 Newton force and a 20 Newton force to a solid object, what is the combined effect? Well, if they act in the exact same direction, pulling together, it's 50 newtons. If they act in exactly opposite directions, fighting each other, it's 10 newtons. But if they act at an angle to each other, the total force could be absolutely anything between 10 newtons and 50 newtons. The physical angle dictates the mathematical outcome.
Because the outcome depends so heavily on the angle, physicists need a very specific definition for this combined effect. We call it the resultant. The resultant is the single combined effect of two or more vectors given in both magnitude and direction by the missing third side of a closed vector triangle. Whenever forces collide or velocities combine in your exam, the examiner is secretly asking you to find this exact resultant.
Okay, let's move into our interactive workshop segment. I want you to mentally put 60 seconds on the clock and do a rapid data scan of this classic practical example, the ship in the river. A ship is traveling due north at 12 kilometers per hour relative to the water. But there's a strong current in the water flowing at exactly 4.0 kilometers per hour in an easterly direction. Your job right now is to extract the core trend. What is actually physically happening here? If you're scanning this data, you should see the conflict. The ship's captain thinks they are going straight north, but the water is relentlessly dragging the hull sideways to the east. If you were standing perfectly still on the shore watching this, you wouldn't see the ship moving purely north or purely east. You would see it moving diagonally across the water. The challenge here is to find the ship's actual velocity, the true resultant, relative to the shore.
And this brilliantly illustrates exactly how we solve it. Let's do a find the flaw exercise. If our rushing student Sam looked at this, he'd probably just add 12 and 4, say the speed is 16, and move on. That is the fatal flaw. You absolutely cannot algebraically add vectors that are at right angles. Instead, we have to use Pythagoras' theorem. Let's do a 30-second speed writing challenge using our PL framework. Point: the perpendicular vectors form a right-angled triangle. Evidence: we calculate r squared equals 12 squared plus 4 squared. That means our resultant r is the square root of 160. Explanation: the resultant speed is therefore 12.6 kilometers per hour. But wait, we aren't done. Velocity is a vector. We absolutely need an angle. We use trigonometry. The tangent of the angle is opposite over adjacent, so 4 divided by 12. That gives us a precise angle of 18.4 degrees. Link: therefore, the final true velocity relative to the shore is 12.6 kilometers per hour in a direction 18.4 degrees east of north. That right there is a 100% perfect maximum mark Peel paragraph.
Moving into Section 4, Resolving Components. This is how we split complex diagonal forces.
If adding vectors is like putting two sides of a triangle together to find the hypotenuse, resolving vectors is taking that hypotenuse and breaking it apart into two clean perpendicular sides. A single diagonal vector behaves exactly mathematically the same as two separate perpendicular vectors acting together simultaneously. In the later, more advanced topics of your Cambridge syllabus, resolving a single vector into a horizontal and a vertical component is an absolutely essential tool for solving complex mechanics problems.
Let's ground this abstract math into physical reality right now. Imagine a glider being launched into the air by a tow aircraft. The two planes are connected by a heavy steel cable. At this particular snapshot in time, the cable is angled at exactly 25 degrees below the horizontal, and the tension force vibrating in that cable is 620 newtons. Think deeply about the physics happening here. That single cable is doing two massive jobs at once. Because it's pulling diagonally, it is pulling the glider forward horizontally to make it accelerate, but it is simultaneously pulling the nose of the glider downward vertically. To solve any exam questions about the glider's acceleration or its lift, we have to split that one 620 Newton force into those two distinct independent jobs.
So the absolutely crucial point here is how we perform the exact trigonometric breakdown without making an error. We mentally or physically on the paper draw a right-angled vector triangle. The tension force F is our hypotenuse. We want to find the horizontal component, which we'll call FH, and the vertical component, FV. Remembering your basic trig rules, the horizontal side that is adjacent to the 25-degree angle uses the cosine function. So the horizontal pull component equals the total force multiplied by the cosine of 25 degrees. The vertical side that is opposite the angle uses the sine function. So the vertical downward component equals the total force multiplied by the sine of 25 degrees. This is the golden rule you must commit to memory for the exam. For any angle measured to the horizontal axis, the horizontal component is F cos theta and the vertical component is F sine theta.
Let's plug those numbers into the calculator and conclude this glider example. For the horizontal forward force, 620 multiplied by cosine 25 gives us exactly 560 newtons of forward pull. For the vertical downward force, 620 multiplied by sine 25 gives us exactly 260 newtons of downward pull. Look at what we've just done. We have proven the massive, tangible value of this mathematical technique. We've taken one messy, complicated diagonal force and completely replaced it with two perfectly clean, independent perpendicular forces. This proves our space mission concept, zero margin for error. By resolving the vectors, we can now independently calculate the forward acceleration using just the 560 newtons, and independently calculate the lift requirements using the 260 newtons. Everything is perfectly structured, organized, and ready for the examiner's green checkmark.
I really want you to let this core takeaway quote sink in. A single vector can be resolved into two perpendicular components, an essential tool for solving complex physics problems. This perfectly summarizes the sheer analytical power of the physics toolkit we've just built together today. If you want to stop answering exams like Alex, who just blindly lists facts without any real analysis, and stop answering like Sam, who rushes the math and completely misses the directional constraints, you need to implement our complete physics answering system. There are 3 unbreakable rules that guarantee top marks on your Cambridge paper. Rule 1, command word decoding. If the paper asks for velocity, you must give a direction. If it asks you to calculate absolute uncertainty, you use the extreme values method. Rule 2, apply the Peel framework. Point, evidence, explanation, link. Structure your math exactly like a logical, undeniable argument. Rule 3, time management matrix. Don't rush like Sam, but don't write endless essays like Alex, where a simple vector triangle and a quick calculation will do the job perfectly.
I want to leave you with a final provocative thought. Next time you step outside and see an object moving through the air, whether it's a football being thrown, a bird soaring, or an airplane taking off, I want you to ask yourself, what invisible vector components are truly driving its physical path? Start looking at the world through this new, highly analytical lens, and your physics grades will naturally soar. Now listen closely. Students who implement these physics strategies see an average improvement of 2 full grade boundaries. But that only happens if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCS and click that bell. Don't let another exam pass you by without having the ultimate strategy in your toolkit. Also, drop a comment below right now with your target grade for physics and the biggest single challenge you're currently facing in your revision. Our team reads and responds to every single comment. Finally, make sure to like and share this video with your study partner so you can both dominate the paper. Ace the Exams. Your Cambridge success starts here. See you in the next one.